So thank you very much. Economics panel, sorry about the delay on getting online here. Really appreciate the great conversation and discussion there. I might invite the panelists to go back to the Q&A and answer those questions during the rest of the conference because you guys didn't get to all those. Okay, so now we're going to transition. We're going to skip over the break because we had a little bit of a delay there for me. And we're going to jump right into the next panel, which is a panel on data transparency, data sharing and transparency. And I met the moderator about a year ago, Ed Otten, because he basically rewrote one of our propagation models in order to do his analyses. And he's been a great leader in terms of developing this panel. So Ed, thank you very much for your leadership here, and take it away.
Thank you very much, Mike. So my name's Ed Orton, and welcome to this panel on data sharing and transparency. Today, we're going to look at some of the solutions, so administrative, technical, and system solutions that hopefully can allow us to do more data sharing and improve transparency in order to improve spectrum management for the future. So I'm hoping that this session is going to be somewhat dynamic and interactive. We have a very esteemed panel of guests who are going to come and speak today. And what I've asked them to do is to provide initial 3 to 4 minutes of opening statements, essentially, on the topic of this panel. And then we're going to go into a kind of interactive session. We have some topics that we'd like to cover. I very much encourage you to post your questions in the Q&A so we can hopefully get to those. And then at the end of this session, I'm going to basically give the opportunity for each of the speakers to say some final concluding thoughts on this particular topic. So without much further ado, I'm going to just cover 3 initial slides just to provide a little bit of background context. So if we could go to my slides, that'd be great. Thank you. Next slide, please. So we know as a community that there's a lack of spectrum data out there. Okay, and there's a variety of reasons for that. So there's national security issues with sharing the data, there's privacy issues with sharing data. We know it's expensive if you and I want to go out and collect that data. And because many of our colleagues in industry are operating in a very competitive environment, it's also challenging for them at times to kind of share the data that we might be interested in, as it can kind of jeopardize their position within the market. So it generally means that we do not have the kind of data that we might see in other industries where data is increasingly ubiquitous. This basically means that we end up with long time delays in how we allocate new bands across the spectrum. And it also means when we carry out analyses where we want to look at the implications of maybe management of the spectrum, we end up using incredibly conservative assumptions in those modeling efforts, in those simulations, in those analyses of the data, etc. Additionally, it also kind of slows the progress that we kind of want to put forward, as Mike expressed in the opening comments yesterday about this kind of spectrum data science future that we all hope that we can kind of engage in. And that's kind of going to change the landscape for us as researchers, maybe from kind of deductive theoretical models to actually using more empirical, inductive-based data where we can use some of those advanced statistical techniques that we're all taking advantage of at the moment, things like machine learning, etc. So, why does this particular context matter, and how do we overcome it? Next slide, please. So it's kind of cliche to say it, but I just wanted to emphasize that all models are wrong, some models are useful, and we're all using models and simulations in order to assess spectrum options. And ultimately, there are inherent uncertainties in the models that we use. We all rely on, at times, assumptions. At times, we rely on monumental assumptions. So really, what I want to emphasize here is that hopefully the better future that we're envisaging actually consists more of actually sharing models, being able to plug and play different models for comparisons, being able to kind of recognize that none of our models are perfect. We are far from that. But by kind of sharing and understanding what's in each other's models, we can push the state of the art further forward. Next slide, please. So whereas that previous quote was really kind of generalist statistical, generalist statistical statement, this one here from Ben Monk, who was long before my time in this field at the Electrical Science Laboratory at Ohio State, he makes this really interesting quote, which I enjoy. It's kind of adapted from a classic Einstein quote, but he says that computer simulations, nobody believes them except those who perform them. Measurements, everyone trusts them except those who make them. And I think that's really kind of poignant, and actually is just kind of a good way for us to kind of address this panel today, because there's kind of this assumption from outsiders that our models are kind of perfect, and the reality is that we're a long way from that. And one way that we can improve how we make decisions using these models is by kind of understanding the limitations of them, sharing better data, being more transparent about our decisions. So I don't want to get in the way of our esteemed panelists, so I'm very much looking forward to introducing them. The first person I'd like to call forward to provide some initial statements is Greg Wagner, who's Director of Strategic Planning at DISA's Defense Spectrum Organization. So over to you, Greg. Please take it away.
Hey, thanks, Ed, and I appreciate it. And thanks, everybody, for spending some time this afternoon. I wanted to focus today on some of the concrete things that we've been able to do in the department to begin chipping away a little bit at this question of data transparency. And I want to just hit three things very quickly at the outset. Some of the work that we're doing in the 2025 megahertz band with the electronic news gathering community, some of the AWS3 work that Howard McDonald talked about yesterday in his opening remarks, and then some of the work under Embers and specifically Path S that was mentioned yesterday. So on the SMCS, or the 2025 megahertz work, the Department of Defense is kind of sharing that spectrum with the electronic news gathering community. Here we were able to kind of understand each other's concerns in the band a priori. And not necessarily a priori from a rulemaking point of view. I'll come back to that point in a minute, but a priori in the sense that the broadcasters were, keen to share with us the concerns that they had about the department entering that band and sharing it, and the department was also keen to understand those concerns, and we were able to establish an MOU that set out a framework for sharing some parametric data about each other's operations, but also set the stage for some joint level testing at both the bench level and the field level, with an eye toward kind of doing some models, predicting some results, and then comparing those results against what we see in the field, and then kind of turning the nerd knobs on everybody's system to find out where things kind of experienced interference, and then understanding each system's response to that interference, so that people could make a judgment about whether that was something that could be worked around operationally, for example, or something that was truly going to be a challenge. And we were able to construct our test reports in a way that allowed a version of those test reports to be shared with the broadcaster community in the case of this band, so they could actually see in black and white kind of our results. So that's one, I think, concrete example. A second one, Howard talked a lot about SSTD yesterday, so I won't dwell on that too much, except to point out that it really did foster a collaborative environment where the department could understand how the carriers were using this particular spectrum, and we could get tangible results. And I don't mean a set of curves. There's a series of papers in SSTD that were submitted as part of ISART. You'll see all the curves there, and those are cool and all. But the reality is, we were able to turn no's to yeses with some of that data. So we were able to wring out that initial conservatism that we had to assume in from the outset of AWS3. But then we were able to back it back out again over time. And then the last item, Mark Gibson mentioned this yesterday in his opening remarks, but that's the Embers and specifically the Path S effort, where the DoD CIO has provided a forum where candid discussions at levels appropriate for national security type dialogues could be had to increase understanding of systems and their behaviors in the bands of interest. In the case of Embers, 3100 to approximately 3450. So just a few observations I want to make on that and try to tie it back to some of the things we've heard about earlier. John Chapin talked a little bit about, or implied a little bit about scale. So these are great, I think, exemplars or pathfinders for us to be looking at. I'm not sure about the scale though. So in the case of the 2025 megahertz, it was just a few pieces of DoD equipment, and we took a crawl, walk, run approach, and we're just in the crawl, walk stage. So we, as my colleague likes to say, we broomed away the complexity to later, and we started with the easiest cases. So promising results. Will they scale out to systems that start to look like warfighting equipment remains to be seen. And then in the case of AWS-3, that SSTD effort has been going on for years. It's a very big effort, and it's been going on for a long time now. So Ed, your opening comments hinted on the time scale there. This takes human resources, it takes financial resources, and it takes temporal resources to make something like that work. And so whether they can scale to machine type speeds or even calendar type speeds, reasonable calendar type speeds, the national security question is always going to be a challenge for the department. As Howard said, we have to dance with the enemy, and it's not just the type of power that we output or the output as it's a system capability. It's how we use the equipment as well. And then we have the further challenge of when we get enough equipment and enough information together in one place, and the aggregate or the ensemble, we have to think about what that means from a national security perspective. Again, the CIO is working this challenge now. I think they've got a solid start with Path S, and we'll have to see how that develops going forward. And the other observation I'll make is with some of these bands, particularly the 3450 and potentially 3100, we have a 5G use case rolling out for the first time. And these some of the use cases we're seeing with 5G are different than the past. So can we use some of these techniques like SSTD as we extend into these new 5G use cases? I don't know yet. We still have some thinking to do in that space. But all of these things have worked. They've worked on time scales on the order of months to years, and it's taken time to gain confidence and trust. How these would all then work in the ISART thesis of this more of an iterative regulatory framework, I don't know. I think SSTD has shown us that we can wring out conservatism, so we can make some conservative assumptions up front and then wring those out over time. I think that what we're doing in 3450 right now in terms of preparing for a sharing apparatus in that band, and the idea of driving that conservatism out going forward will be another great test case. We'll see what that band looks like, perhaps at ISART 23. Again, Embers and Path S given us some indication of what a kind of a human-based conversation approach to data sharing and data transparency. So I'm really looking forward to hearing from the other panelists and tying this back into this notion of a iterative regulatory fabric with all of the concerns that we heard about in that end. So thank you, Ed.
Thank you very much, Greg. And it's Very exciting for me now to introduce Kaushik Chowdhury, who is Professor of Electrical and Computer Engineering at Northeastern University. We would very much like to thank Kaushik for being a superhero today and standing in at last minute. Johnson was unable to attend this panel, so thank you very much for that, and we look forward to your initial statements. Thank you.
Thanks, Ed, and thank you for having me here. So I'm going to present a different kind of a talk, and this is going to be more on what exists as a community resource that academics like me can use. And also, I'll point out to some methods and techniques which I think can overcome some of the privacy issues that are plaguing the sharing of data sets. So next slide, please. So I'll leave my introduction aside broadly, but I've been involved in a number of these different large-scale projects, both supported by DARPA and NSF and IARPA. And in many of these, data sets are key. And when I talk about data sets, they are generally IQ data sets, and sometimes sharing them becomes a big problem. So we recognize that there needs to be a venue where researchers can go and collect data sets for themselves and then do machine learning type of work on them. So I just want to highlight one of the projects that is sponsored by the National Science Foundation. It's called as RF Data Factory. And we just kicked it off. In fact, we had a workshop, and you can click that link and you'll see the program that we just concluded last week. So this is a platform for accessing and sharing RF-centric data sets. And what we have done here is that we have made available data sets. We have provided sort of a concise way to look up data sets of interest. We have made available software tools and APIs that sort of democratize the action of collecting data sets for yourself, as well as various tutorials where we train the community on how best to create data sets and how to use standardized metadata representations for them, etc. And I'd also like to connect very quickly with some of the other interesting sources of data sets. So one of them is, again, the National Science Foundation's Power Project, the platform for advanced wireless research that allows you to go ahead and capture data sets at scale, as well as the Consortium, which started out under the Spectrum Collaboration Challenge by Paul here, who will probably speak right after. But then it has since transitioned as a community research resource, where from a competition environment, now you can go in and use it in a research environment and actually create very rich interference scenarios and collect data sets. I'll provide you some examples of these in just a bit. So next slide, please. So what these data sets are available under RF Data Factory today? So if you go to the website, you will find a classification diagram like this. And as you click one or more of these, so for example, radar or Wi-Fi or cellular, as you click on these, a menu of data sets appears that tells you that this is what the data set available is, and here are some of the use cases. And when you click on it further, it gives you access to a website which clearly lists the metadata representation and so on. So this is really a community resource, an example of data sets organized that people can use. The next slide, please. What software resources are available? So we believe that it's not just raw data sets, but also ability to create your own data sets or even create standardized metadata representations. So we have tools and APIs that allow you to go in and collect, or create SIGMF standardized metadata for collected data sets, visualization tools. Tools, for example, you can create these new architectures like Open RAN architectures within the Consortium environment and collect data sets just for that sort of environment. So this is called Scope. There are a number of other APIs, and all of these are on the website. Next slide, please. We believe in community training and education, and because this is a fast emerging field, I just put on my professor hat, and and whenever I look back in my wireless mobile networks courses, I see a gap between what we teach as part of regular communications and wireless versus things which are more hands-on and practical, the action of collecting data sets and the challenges involved in creating data sets that can lead to reproducible research. So we have a lot of tutorials all online and made available as part of this effort. Next slide, please. Here are some thoughts, and just to seed some ideas as the panel discusses this forward. So question is that what can we do to facilitate data sharing? So one way in which we should think on as a community is what technical or transformations can we do at the input source itself? So for example, instead of IQ data that you see in the top part of the slide, instead of this just raw IQ pipelines, could we create spectrograms and hand out the spectrograms a little bit more freely than we would IQ data? Could we share features and not raw data? So here's the second piece out here in the slide. The second image shows you a typical neural network. So if I take these multiple layers and if I just slice them just before the last layer, which is the softmax layer, what you get is an intermediate feature representation. It's not raw data anymore. So where should I slice that neural network to share features? And can features then be shared more generally than raw IQ? So this is something that we should think about. What are the challenges in reverse engineering these features and getting back perhaps more privacy intrusive inputs? How generalizable this method is, and can we really extract features and share them as a generic way to share input data without the raw data itself? And then finally, just a thought to the community that we have rallied behind the SIGMF metadata format. I know the NTIA is heavily invested in SIGMF too, but are there, or is the standard sufficient to capture challenges of time varying and adaptive signals? So once I create a schema, can the schema evolve or capture evolutions of the signal over time, especially for various DoD use cases where a signal can have many different actions and interpretations? So that's all I have. Just wanted to seed some ideas, and we'll look forward to more of the interesting discussions. Thank you.
Thank you very much, Kaushik. That was excellent. So now I would like to introduce Eli Cohen. Eli is coming from Palantir, and he's a deployment strategist with a technical background in software and hardware, and I'm very excited to see the analytics proposals that he's going to present in this initial session. So please take it away, Eli. Thank you.
All right, thank you, everyone. You can go to the next slide, please. So as Ed said, I work with Palantir. We work with a lot of different customers through USG and also commercial that are trying to get value out of their data. So I wanted to use the lens of this panel talking about data sharing and transparency to talk about why is that a problem, and then what are some ways that you can solve that. And I want this to be kind of platform agnostic. So these are Palantir branded sites, but for the purposes of the panel, this is all right. This should be quite generalizable. So when I think about data sharing, and I'm often in the room with people that are trying to convince other people to share data with them, there are two major issues that come up. The first is privacy and security, and the second is the what's in it for me conversation. We work with a lot of customers that privacy and security are paramount sort of to their existence. If you look at some of the letters and acronyms down on the bottom right there. And so having support for being able to work in a SIPR or a NIPR environment to actually facilitate this data sharing, things like FedRAMP accreditation, where the government says, yes, we trust that system to take this data in and operate at that security level and propagate those markings, is a really critical piece. The other side of that is also from a data stewardship perspective. How do you make sure that that data that's being shared is being used correctly, being exposed to the right people? Can you audit who's accessed that data? Has it ever left a system? Who's touched it? Those are really, really important questions that always come up when you're talking to somebody that says, I want to give you my data, but as soon as it leaves sort of the walls of my organization, what guarantees do I have that it's going to be treated with the same care and respect that it has within my walls? On the other side of the coin, the what's in it for me, I think it's a really interesting really interesting conversation. I like to think about it in an ROI framework. There's an investment in data sharing. That can be, okay, I'll set up an API for you to call, and that's really easy, and that's all I have to do. I don't have to think about it. I don't increase my IT spend. Or I'm a particular RF shop, and we do all of our data storage in this one format, and you're requesting it in a different format, and now I have to go through this transformation process. So there are clear differences in level of effort that it takes to even participate in the data sharing in the first place. And then the second part is the return part of that, which is, what do I get back from that? And so when we think about the tooling necessary for data sharing, you will not get data sharing to happen unless there's value that comes back from the data sharing. So the first part is, how do you convince people to show up to the table? By providing the right security protocols around it, auditability, things like that. And then what are the layers of actual things that people want to do with it that make it valuable for them to put their data in the first place? And so when we talk about platform capabilities, there are really 4 blocks. There's the data integration, management, security piece, which is that core of, you have to treat data correctly. And then everything that happens after that is value add. Next slide, please. So the framework that we've been thinking about, as informed by some work with a customer I'll talk about in a minute, is really about, how do you create a framework that respects those permissions, that ties into the right organizations, and that can provide value and security for everyone at the table, right? So it has to be able to work in the RF environment that we see in the world around us, which isn't just commercial systems. It can be DoD systems, right? And you leave those off the table, and there's a lot that you're missing. This whole concept of, how do I know that my model and the way that I agree, the way that I see the world agrees with the way that you see the world, right? How can we actually have a conversation with data about modeling capabilities? And then finally, when you want to look at something like, I've got an emitter and I've got a receiver, and they might come from different organizations with different information, how do I look at those holistically in the same place? So one of the experiences that we've been really fortunate to have over the past 6 months or so is supporting the FAA on the 5G rollout. It's been pretty fascinating to see the mechanics of all of that going on, and what that really looks like is telcos actually sharing to the FAA, these are the locations of our emitters, this is where the beams are pointed, this is the antenna pattern, and feeling comfortable sharing that because they know that there's significant access control around that data. That goes into a unified modeling environment, and then the thing that they get back in a very, very quick turn analysis is, you said you wanted to turn on these 10 emitters. Maybe think about turning that one down by 2 dB, or rotating that one this direction, or turning that one off completely, and actually going and monitoring that process. So speaking to some points that previous panelists have raised about this iterative cycle, moving quickly, it's really, really critical to be able to create that value add for an organization like a telco to get something back from this data sharing, to be able to do things faster, and to create smarter investments. So I'm really looking forward to the rest of the panel and the discussion so far. Over.
Thank you very much, Eli. So just before we progress, if the other speakers could just turn their microphones off if they're not currently speaking, that would be fantastic. Thank you. So I'm very excited to introduce our next speaker, which is going to be Paul Tilghman from Microsoft, who is currently the Senior Director of Azure Spectrum Technologies. So Paul, over to you. Thank you.
Good afternoon / good morning, depending on where in the US you find yourself today. Really excited to be back at ISART, or at least virtually back at ISART, with so many familiar faces. So no slides. What I wanted to do is, just in a few minutes here, open with really 2 different vantage points and some trends that I'm seeing in terms of what's happening in the cloud world that I think really starts to form the underpinnings of what next generation spectrum management looks like. And so first, let me just start by saying, in my role, one of the things that I think I really benefit from that I think can maybe help open this conversation up a little bit is that when we talk about the intersection of spectrum technologies and the cloud and a platform like Azure, I get the joy of looking at it both terrestrially and non-terrestrially. And so I think often at ISART, we find ourselves talking about spectrum management from a very terrestrial-centric perspective. And I actually think some of the most interesting challenges in spectrum management are coming out in the non-terrestrial world. Interactions, excuse me, between low Earth orbit and geosynchronous orbit satellites, for example, or in the interaction between terrestrial and non-terrestrial use of the spectrum. So the C-band auction recently clearing spectrum in order to make more terrestrial use for 5G, and then challenges in the 12 gigahertz band over terrestrial versus non-terrestrial use. Do we deliver more satellite communication, or do we deliver more terrestrial ground 5G communication? And so I think if we zoom out from that, one of the things that we really need to look at is, what are the key ingredients for a platform that enables next generation spectrum management, whether it's terrestrial, non-terrestrial, or the interaction between the two? And my supposition is that cloud is central to all of these. That could be Microsoft's cloud, that could be Amazon's cloud, that could be Google's cloud, that could be a private cloud. But the idea of distributed compute that is geographically global, I think, is a key underpinning to how we approach spectrum management in the future. So 3 key areas that I want to focus on and just highlight a few industry trends that I think are useful as we move this conversation forward. First is a platform for acquisition of data and metadata that tells us what the spectrum is being used for. So I've got to get data about my world to know how I might want to even start to think about changing what I'm doing and affecting different outcomes. 2 is then a series of standards for storage and distribution of that data, as well as a platform for knowledge mining. So I have to be able to, whether that data is data in motion or data at rest, I need to be able to store and distribute that data in well understood standards. And then ultimately, that data is only as useful as I can mine information out of it. A spectrogram isn't particularly useful. A series of spectrograms that traverse an entire year for a geographic region with other exogenous data sets that let me know what's happening within that geography over that same period of time, that's useful, and you can mine knowledge from that. And the last key ingredient here is a platform to actually take action on your observations. So if you have data, if you can store, distribute, warehouse that data, and mine knowledge out of it, that's only useful if you can then do something about it. And so, as I said, I think the cloud is really central to each one of these areas. So let me focus on acquisition first. A major industry trend that's emerging is that data centers are now becoming antenna farms. Microsoft, when it builds a new data center, when it builds a new cloud region, we now do a full RF assessment, civil engineering assessment, et cetera, in order to actually build antennas on that data center. Now, we're doing it today to turn those into Earth observation ground stations to downlink data from space. But my point is that the civil engineering work and the RF work is going into turning the global footprint of where our data centers live into an apparatus for collecting RF data. Highly related is that we're now seeing tier 1 telcos, 5G, 4G, et cetera, migrate to public cloud. And this is very much changing the definition of what the cloud is. We would have traditionally said cloud are megawatt class data centers that live in a few limited geographies. Microsoft has about 60 of them globally. But now the cloud is a geographically dispersed concept. We have the far edge, the radio unit, the distributed unit are now really a part of the cloud. The near edge that contains the CU and 5G is part of the cloud. Regional data centers that contain the core, part of the cloud. So we've gone from just a single handful of hyperscale data centers to this geographically dispersed computing set of assets that cover a large geography and provide, again, an apparatus for collecting data about our environment. And the last thing I want to touch on here is the democratization of data. Some of you that, if you think way back into your brains here, might remember something that Microsoft ran called the Spectrum Observatory, a project I think was well before its time, and it mounted to basically a server and an old school, I think it was a USRP1, that you could go deploy on your property and collect information about the spectrum. I think that the time is right to think about recreating the Spectrum Observatory in a cloud-centric fashion where modern radios can be distributed, data streamed to the cloud, and automatically stored, archived, warehoused, and analyzed. That gets me to part 2 here, industry trends, and that's standards. I think we're starting to see the industry normalize around a handful of standards. Let's focus on data in motion at first. In order to bring data into the cloud, we need ways to standardize what that data is. It's very simple to say, like, oh, we'll collect IQ data. How will you collect IQ data? Is it interleaved? Is it 16-bit? What's the provenance of that data? Where did it come from? How was it collected? What was the hardware? All of these are important questions when you're actually collecting the raw data in the first place. And so Microsoft and a number of others across industry have recently formed a consortium called DIFI, the Digital IF Interoperability Consortium, focused on adopting a standard that basically says, here's how cloud providers will ingest IQ data into the cloud in a raw streaming fashion. So we now have an industry standard that says this is how the cloud will interact with RF sensors. That's great for data in motion. What about data at rest? Kaushik already hit my favorite that we're seeing growing industry adoption across the community, and that's SIG-MF. I think SIG-MF is well poised to be adaptable over time, extensible, and we're now even building native tools on Azure to go directly manipulate SIG-MF on top of the cloud without having to go in and out of intermediate file formats, as an example. The last thing I want to touch on here, so if I have standards to ingress and egress data from the cloud, if I have standards to warehouse data on the cloud, I now need to be able to actually mine information out of the cloud. And that's another area where it's easy to think about creating relatively small machine learning models, things that fit within a single GPU, and hope that we'll extract a lot of information about the spectrum from these. What I want to challenge is that the scale of models, AI models that are really doing important things in industry has become so big that you really cannot train them unless you're training them at cloud scale. GPT-3 is 175 billion parameters. Last year, we announced a model called Megatron Turing, which is 530 billion parameters. These models are capable of understanding over 100 languages natively and directly translating between them. These models are capable of working in multiple modalities at once. So I can say something like, I would like a photo of a cat wearing sunglasses on a beach at night. And it can actually synthesize between human language and create that image. This kind of ability to take multimodal data and natural language and intermix it so that we can not just have the data, but ask questions of the data is key. Otherwise, we just have a lot of data and we have a hard data mining challenge. The last thing I want to point towards as an industry trend here is the ability to take action on data. The reality is that all modern tier 1 telco networks are being built cloud native. That is, rather than hardware, they're being built out of a series of containerized network functions that are geographically distributed across data centers. The space industry we're seeing is basically learning from the last decade of the terrestrial wireless community and is following suit. That means that whether it's terrestrial wireless or non-terrestrial wireless, that means communications is basically adopting the same CI/CD muscle that we see today in other software technologies. So my telco network in the future will have the same daily, weekly rollout of new features that we see Office 365 do today. This CI/CD muscle becomes our action loop for how we do and manifest spectrum management. It means that the network will always be evolving and changing, and that becomes our entry point to take what we learn and put it into action. So with that, I'm looking forward to the rest of the panel.
Fantastic. Thank you very much, Paul, for those thought-provoking comments to start us off. So without much further ado, I'd like to get into our final panelist, which is Ian Fogg, who's VP of Analysis from OpenSignal. Over to you, Ian.
Great, thank you. So I have a few slides. A few just on who we are, what we do, and then I have some slides on some actual real-world data, looking at what's actually happening with mobile experience and spectrum in a few different ways, looking in the US. So next slide, please. OpenSignal is an analytics company. We do all the measurements, but we do a lot of scientific analysis to derive meaning from those measurements, which is critical. Those charters, our methodology, they're all on our website. Next slide, please. Next slide, please. Thank you. We do all the kind of technical measures. I think the panelists so far have talked a lot about signal measures. Signal is essential to understand spectrum and what it means for the experience, the users of that spectrum, but it's not sufficient. What we have been doing at OpenSignal is taking those foundations of technical measures of signal, speed, latency, and looking at what it means for uses of that spectrum. So in the consumer space, that might be video streaming, multiplayer gaming, voice communications, or most notably during the pandemic, group video calling, which is essentially what we're doing today. When we look forward, the cellular technologies, the 5G technologies, which some of the panelists mentioned around some of the spectrum bands that are currently up for debate, 5G will power not just the consumer part of the economy, but increasingly the economy as a whole, as the carriers and the telecom vendors move into smart agriculture, industrial automation, automotive connectivity. It's really a glue for all parts of the economy. So it's one of those things where to understand how spectrum, what value it has, is critical, not just for consumers, but for the wider economy going forward. So I have some examples here. All of these are published on our website, so you can look at them later and dive in. If you get the slides, there's a link on each slide to the source material, which has got additional data, additional analysis. If we want the first one of those, next slide, please. One of the things we published recently that we looked at was how C-band, how it's actually affecting the user experience in the US. There are two charts here. On the left, you can see the actual speed for upload and download through C-band on two of the US carriers. And we've contrasted that with the 2.5 gigahertz spectrum the other carrier has been using for a similar kind of purpose. On the right, you can see the jump in the overall 5G download speed around the time one of those carriers launched C-band. So I think we're all very acutely aware that C-band has been quite a challenging rollout in the US, with a lot of debate between different sectors of the economy about how to clear the spectrum, when to do it, how to manage power levels and the rest. The good news is there is benefit to the new users of the C-band spectrum in the US. Next slide, please. We've also looked at one of the other spectrum models in the US, CBRS. This is data collected from smartphone users. This is all 4G data. On the left here, you can see how a number of spectrum bands, the power level that the end user device receives diminishes with distance from the tower. On the right, on the 3.5 gigahertz, you can see power levels are generally much lower. So one of the other kind of key things that we see in the world as we talk a lot about spectrum is a very widely varying asset with very widely varying benefits. And understanding the characteristics of each type of spectrum and what it means for the use of that spectrum is really, really important. On the right-hand side here, you can see that those power levels correlate very closely with the end user's speed that users had at the same distance buckets from the tower. And you can see on the right side, there was a particularly large fall off in speeds on CBRS, partly because LTE, 4G technology, wasn't really designed to run on that high frequency spectrum, which is one of the reasons why globally 5G NR is being used at those frequency levels and is opening up many of these new spectrum debates on spectrum above 3 gigahertz. Next slide, please. We've also looked at unlicensed spectrum. On the main chart here, you can see multiplayer gaming. We've compared that with two types of 5G spectrum: millimeter wave, this very high capacity, very high frequency, very localized spectrum, with the overall 5G experience, and with 4G. We've also split Wi-Fi out, because one of the key things you can see with unlicensed spectrum is different kinds of Wi-Fi have different characteristics. Public Wi-Fi is typically in a very noisy environment. It's typically a place where you have a lot of Wi-Fi hotspots in close proximity. Other Wi-Fi on this chart is typically residential. So it's Wi-Fi attached onto the home broadband. And it's typically a much better experience because you have less interference on that unlicensed spectrum, because the residences tend to be further spread out. On the bottom right chart, you can see an even greater difference when you look at the speeds. And you can see public Wi-Fi is a fraction of the speeds of residential Wi-Fi in the US. But you can see also that 5G using licensed spectrum is considerably faster than public Wi-Fi, and in the case of millimeter wave, considerably faster than residential Wi-Fi as well. So we can see with open signal data, different kinds of spectrum, different kinds of models, whether it's unlicensed, licensed, or shared licensing. And we can see some of the real characteristics of how they're actually being used in the world, looking not just at the signal measures, but some of the applications and services and experiences that people are using to move just beyond the technical measures to the overall experience end-to-end of users. Next slide, please. We can also track just macro topics. This is a piece we published looking at just the overall 5G experience across the US, where there's wide varieties in on how 5G is being deployed, how extensively, what the quality of experience is. Partly this is just the state of the rollout. We're still at a fairly early stage, but partly this is related to the very complex spectrum picture in the US. In some countries like in the US or in Brazil or India, spectrum is not a national asset, it's not a national license. In the US, it's very fragmented, those spectrum holdings, and that has a direct effect on the 5G and the cellular experience of users. In some markets, spectrum is, licensed nationally, and it's a much simpler picture. But again, we can see those granularities, those variances in the experience, often determined because of different spectrum holdings when we look at the overall experience across the US. And again, there's more of this on our website. That's my opening remarks. I'll hand it back to Ed so we can jump into some discussion.
Thank you very much, Ian. And I really liked seeing those visualizations of real world quality experience. I think that really kind of enhances the debate that we're having. So I do have a couple of questions that I want to kind of start us off on. I just want to first go back to Greg, and I want to ask about what appetite there is for MOUs, and can you talk more about how that kind of data process kind of took place? And then I'd like to go to Kaushik, please, because obviously, Kaushik, you're on the kind of data generation side. And I guess my question is how you kind of validate the synthetic data sets that you were generating, and whether you've had, whether you could use data under sort of MOU arrangements to help improve your existing framework that you're developing. So Greg first, and then please Kaushik.
Ed, yeah, thanks, it's Greg. I didn't quite catch, you dropped out right there. You wanted to ask me about the appetite and then I lost the audio.
You mentioned in your initial statements that you've been involved in MOUs for data sharing. I think you said it was parametric data, essentially, so you could help them parameterize your models, your analyses. Could you talk more about that process, please, and talk more about the appetite, whether there was strong appetite for that or whether it was quite a hard process to actually go through?
And so I'll answer the second part first. It was a kind of a lengthy process, and that's and I don't take this the wrong way, but there's a lot of legal review there. So that takes time, and so while it might, the action officer level, the technologists might have had a general agreement, it might take months and months and months to codify that agreement into something that both parties can sign. I don't know what you do about that, but at the technologist level, I think, well, even under the 3450 work that we're doing now, the department is very keen to get MOUs or non-disclosure arrangements in place for the licensees there, so we can hear from the licensees, understand how they plan to use that. And the last gentleman, Ian, kind of mentioned there's no national licenses, so these, we have to deal with these things locally, which increases the number of conversations we have to have. But how are you using this so that we can be in a better position to model the interference as early as we can? So we don't want to assume everybody is using it the same way everywhere, and then have to drive that conservatism out. If we can, we'd like to represent that as quickly as possible. We have to make sure that the carrier's data is protected. This is a lot of secret sauce that's involved here, and it's important that we have the right protocols in place. I would say there's a lot of appetite in the department to have those exchanges. But I do think it takes a little time to make sure that the proper protections are in place, not just for the initial exchange, but kind of understanding how the data can be distributed, what happens, when we're done with the data, do we retain it? What happens to the data as it gets baked into a decision that the department makes, which then forces the department to deal with a records management set of rules. And so now we have to hold on to that data for a certain amount of time to meet statutory and regulatory requirements in records management. So there's all kind of interesting second and third order effects here that we just have to be careful of. And I think that's why it takes a little bit of time to nail those up. But once they're nailed up, they seem to work really, really well.
Fantastic, thank you. And I think we have about 8 minutes left before we're going to go into the final remarks point. So Kaushik, if you could just speak for a couple of minutes, please, about the validation and whether more data, more MOUs might be useful for you.
No, absolutely. So the mantra for machine learners is more data you have, I'll grab it, right? So that's the way we go with it. I'll give an example of the RIFMLS data set. And so we did a lot of interesting technical works that we used the RIFMLS data set for. This was the Radio Frequency Machine Learning Systems program from DARPA. Again, Paul is here. He was a program manager. So we did a lot of interesting technical works that we wanted to tell the community that, look, this is how we do it. But Paul would scold me for sure if I would release his RIFMLS data set. So what we did was that we collected our own data set, which was not at scale of terabytes, but it was somewhat smaller. But we did it in an RF anechoic chamber. We did it inside in a 2.4 gigahertz lab with proper precautions. So we validated results on both the government submitted RIFMLS data set that we would not release, and then our own data set that we would release. And guess what? The industry started to pick it up. So if you look at the deep learning toolbox that MATLAB brings out, it uses our RIFMLS data set to showcase their algorithms. The Q signal from NVIDIA uses our RIFMLS data set to validate their signal processing algorithms. Now, this is possible if we could establish a one-to-one relationship between the quality of data that we could share and what we could not share. And we made sure that everything from metadata representations to diversity of data captures, these were all relevant. So I think we need to invest a lot of time in creating good data and then validate against benchmark data, which you may or you may not be able to share.
Thank you very much. So I'd like to just go to this question that was in the public Q&A box, which is from Richard Bennett. And he's asked, what can we learn from the fact that 5G radically outperforms Wi-Fi? And that's in your presentation, Ian. So I'd quite like to go to you so you could take a minute, and then I'm going to go to systems and models with Eli and Paul. So over to you, Ian.
I think it reflects a few things. I think it reflects the challenges of unlicensed spectrum. I mean, there are many benefits in unlicensed spectrum: the flexibility, the versatility, But there are clear benefits with licensed spectrum as well in terms of providing a great quality of experience. I think the other piece to be aware of here is that that slide was in the US, right? And the US has, with the exception of millimeter wave, it's not been a leader in 5G. There are much better 5G experiences in other parts of the world where there is significantly more spectrum available for 5G. So I think one of the other learnings here is that's in a market where spectrum has been in really short supply for 5G, and where the carriers have had to manage uncertainty about how quickly they can deploy things like C-band.
Thanks for that. And I think when I saw your slides, what I kind of took away from it was that Wi-Fi seemed to be having those problems in public settings where maybe you have coordination issues and lots of interference. But then actually for the kind of home Wi-Fi setting where Wi-Fi is incredibly cheap to deploy, it seemed like it had much better performance. So maybe those public cases.
Yeah, I think so. I think there's another piece here, which is, you know, if you want to get the benefit of one of these technologies, you need to make sure everything is in place. You need to have the end user devices capable of supporting that latest standard. You need the network supporting it. You need the backhaul supporting it. And one of the challenges with Wi-Fi is that Wi-Fi devices tend to have much slower replacement cycles than do cellular devices. So even when you roll out the new standard, it maybe isn't deployed as quickly or as ubiquitously as maybe our cellular experience.
Thank you. So now I'd like to turn in just the last 4 minutes while we're on the open session to Eli and Paul. And I'd like to get your thoughts, please, because you both presented ideas on how we could have system solutions to overcoming, you know, maybe our lack of evidence on spectrum across time, space, frequency. Could you just talk a little bit about the barriers in maybe implementing the ideas that you put forward, please?
I'll maybe just tackle one, Ed, and then we can add others in. But one that I see is that we often end up with a position where the technical incentives and the technical what's possible do not align with business outcomes. And then a lot of times the gulf between business outcomes and technically what's possible actually betray an underlying gap from a policy perspective, right? So if I pick on, you know, CBRS, right, I would say that if we wanted to go recreate CBRS in another band, what exactly are the business incentives to go create another type of spectrum access system, especially one that's maybe more complicated, more sophisticated, and costs more to run? Those really don't become clear until policy has cleared the way for the band or that spectrum access system to be in use. So it took 5 years to kind of get the policies around CBRS right? So now we have CBRS. And I think because it took 5 years to get the policies right, we also have a lagged private 5G market where there probably isn't as much private 5G out there in the world as there could be or should be, because who is going to invest in building, you know, in a substantial way private 5G technology, not knowing where the spectrum would come from? And so I think the ability for regulators to sort of accelerate the regulatory frameworks so that then business decision makers can say, yes, this is worth investing in because it will go create real business opportunity, revenue drivers, that's kind of a must. Otherwise, we'll always do regulatory first, and we'll always be somewhere between a decade and a half, decade behind where we could be, just because of the speed of regulation.
Thank you very much. And Eli, over to you.
Yeah, I'll piggyback on everything Paul has said. You know, there's the regulatory part, and then coming back to his first points about being cloud native and thinking about platforms. I think one of the interesting trends that we've seen over the past decade or so is as it becomes easier and easier to get resources in the cloud, and as more open source projects exist to do small pieces of this overall sort of spectrum analysis, spectrum management piece, the democratization sometimes leads to fractions as well. Right, so we might see people on forked versions of models where there are slightly different variations on them. They're using data storage that maybe isn't compatible with other pieces. And so things that have made it very, very easy for players to stand up their own cloud interfaces and to put data in the cloud and to move their analysis to the cloud has led to a proliferation of cloud systems, which is in fact a pretty big challenge as well. And so there's an argument that could be made around what's the right balance between everybody having the ability to go and spin up resources to train a gigantic model when they need it, but to also have that march along with the rate of iteration that we see in this, as Paul said, the sort of CI/CD world of things do not stand still for very long, right? How do you make sure that you're remaining performant over time? And so I think that coming back to some of the discussions that we've had about standards, about how do you share information with each other, how do you do that in a way that's responsible and actually passes value on down the value chain, I think it's a really interesting discussion, and I hope we'll see some interesting work in the next few years on how to action this.
Thank you. And I think, from what we've just kind of discussed in this session, I'm very optimistic about the future. I'm glad we're talking about these cloud native system solutions, because I can see how the evidence base could be generated. And I think that that's a good first step, even if it takes us a long time to kind of deliver on that vision. So we've got 9 minutes left. I'm going to ask each speaker, please, just to provide 1 or 2 minutes of quick kind of conclusionary comments. And I'm going to go through in the order which we went through. So Greg, if you want to just round up your thoughts, it'd be great to hear what you think. Thank you.
Well, thanks, Ed. I wanted first to maybe highlight the comment that Eli made earlier on the, kind of the trust dimension and the return on investment question. I think that was I think that's central in the case of the 2025 megahertz band that I spoke of earlier. The DoD wanted access to the band, so our motivation to share data was to gain access to the band. Whereas in AWS3, it was kind of flipped a little bit. We got to say no, and so the carriers in some cases were motivated so that they could get a yes answer while maintaining the DoD's risk position. So I think that's good food for thought going forward as we kind of contemplate this. I guess if I had to wrap everything up, I would say that we've got some models, Ed, that we can work from going forward. I think that it sounds like there's a lot of effort that's being put into standardizing some data platforms. We've had success in sharing the data, but as I indicated, we've got some some time challenges here. These things are working on scales of months to years in some cases, and they're resource intensive, but they do provide some pathfinders that we can use. And in the end, I come back to that same question. We do all this data sharing, we develop all these standards, but to what end? I mean, do we get a coordination zone that's set at 100 kilometers, and after 36 months, we can revisit that and shrink it to 50 kilometers? Does that turn no's to yeses? And can we be articulate in how many dBs are we off from a no to a yes?
Thanks, Greg.
1 dB, how much difference will 1 dB make? And those are business decisions as much as they are technical decisions. Thank you.
Thank you very much. So I think we're going to have about 1 minute left per person. So, Kaushik, please, your final thoughts.
Yes. So one thought that came to mind is that we should think about data, RF data, going beyond RF data. So to me, data would be multimodal. You have visuals, LiDAR, cameras. All of this will augment, if not provide context to RF data. I think that came out in the panel. I'd strongly advocate for that. The second thing is training. Data collection and utilization of data is as much an art as much as it is a science, and we must invest in our training pipelines, education, and workforce development to really bring out that the next batch of engineers. So I'll pause here in the interest of time. Thank you.
Thank you, Eli.
Okay, I'm going to auction the remaining 3 minutes between Paul and Ian. So look, I think what's really interesting about this panel is that everybody's coming from a different perspective, but we're all talking about the same fundamental thing, right? The RF environment. And I think that until everybody that has a stake can look at the same picture, and Ian can do his analysis, and Kaushik can run his models, and Paul can enable the cloud part, and Greg can run the defense sector on this piece, it's going to be a scattered environment. And so I think that this panel is in some ways a microcosm of the world, and hopefully more proactive communication like this can happen. Over.
Thank you, Paul.
All right, if I were to wrap up here, I think something that I would love to see emerge over the next 1, 2, 3 years, maybe no more than that max, is I'd love to see a moonshot program in spectrum management come out of, pick the appropriate part of the government. Something that unites academic researchers, something that catalyzes real practitioners, something that also provides clear, obvious business value. Because I fear that we will be arrested by a number of the challenges in trying to figure out what data do we need, how do we need it, where do we need it, to what degree does it need to be multimodal, how do we distribute it, what problem are we solving? Like, all of those challenges will continue to, I think, arrest the community. And if I go back to the one clear example in CBRS that we have, the problem there was easy to solve and straightforward because the incumbent was well known, well understood, and it was clear how to model them. If we want to move beyond CBRS, I think we need a sort of uniting moonshot program that brings industry, academia, and government together to solve that problem.
Thank you, Paul. And over to Ian. We've got 1 minute left.
So I think what I heard from the panel today is data alone is not sufficient, right? Whether it's Kaushik talking about machine learning models, Paul talking about the capabilities of Azure Cloud, Eli talking about Palantir's capabilities, that you need to have the data, you need to have the measurements, but you need to apply meaning to them. How you do that requires data science expertise and, you know, all those kind of general purpose skills that could apply in any industry. But you also need to have the specialist knowledge about this industry and about these characteristics as well, and tie those together. I think also, to look at the different uses of the spectrum, you need to understand different industries, the existing users of different types of spectrum, and the potential uses as well. And together we need to kind of allocate spectrum efficiently between those competing demands. When I look at the US and I compare it globally, it's a really complex picture in the US, and it's holding the US back at the moment. And I think one of the things that we need to do in the US on spectrum is be faster and more efficient at allocating spectrum well. And I think if we don't do it as an industry, there'll be external pressures from politicians, from consumer groups, from large industrial conglomerates for us to do it better. That's my immediate observation, I think, here.
Fantastic, thank you very much. Well, I guess this is, our opportunity to kind of round everything to a close. And I know that I'm biased, but I actually found the discussion today very inspirational. And I think it really sets out a nice agenda for each of us in our respective areas to improve, data sharing and transparency in the future in relation to spectrum management. So without further ado, I guess we're going to end this session. So thank you very much for being here. And we look forward, hopefully, to seeing you all tomorrow at the next session for ISART 2022. Thank you, goodbye.
Well, thank you very much, Ed, and the panelists from the data sharing panel. I was pretty amazed at how we closed that out with all the summaries, and all the way back to Evan and the economics panel too. I felt like this was a great day, and with some really bright ideas that came out of it. So I want to remind the moderators that we're to come back on the last day and try to recap towards a roadmap on policy innovation and spectrum around these around continuous evolving science between in spectrum regulation. Tomorrow, Howard is going to kick things off at 1 o'clock Mountain Time. So please enjoy the rest of the day, and we will see you tomorrow at ISART.